In this video, we're going to go over the methodology for indexing cubic structures, and this is what I like to call a manual indexing method, because we're able to do it, we can do it on scratch paper, but more likely on a spreadsheet. So this is a very simple method that you can use to index cubic structures, and so this is what we're going to start with. So I want to go over the equations and so forth before we just sort of jump right in to indexing this case. So the equations we're going to need, as always, we're going to start with Bragg's law. So we have, n lambda equals 2d sine theta, and I should put HKL for the d value here. And we're going to ignore or say that n equal 1 so that we more or less can ignore it. Since this is cubic, we can also use the equation for interplanar spacing related to the lattice parameter. So we have this equation. To make our life sort of simpler, we're going to define the sum of the squares in here as s. So this is h squared plus k squared plus l squared. This just kind of simplifies things for us so that we have this. And we're going to combine these two expressions because this is going to help us take our experimental data and get everything from the experimental conditions on one side and then constants on the other side. So if I sort of combine those, I have this. And then if I do some rearranging, and you'll see where this rearrangement comes in a little bit later, but let me just go ahead and rearrange it for you. So we have sine theta and then we bring over the s, and lastly we have sine squared theta over s equals lambda squared over 4a squared. All right, so the important thing to kind of note about this part is the left side here with the sine squared theta over s. These are this is basically everything related to the experiment. So the angle and the values of h, k, and l. So that will depend on the given peak. And then over here, you'll notice that the wavelength and the lattice parameter, these are constants for the expression, or for the experiment. So if we're looking at a single material that doesn't change crystal structures during the experiment, then this should be the same. We don't change wavelengths during the experiment. So this part changes based on the diffraction peaks, and then this part remains constant. So that's going to be important for us moving forward. All right, now I'm going to go over the steps for indexing cubic patterns using this manual indexing method. And then once we have the steps down, we'll go through those in an example in a Google Sheet. So let's go through the steps required. So step one, what we do is we assume a specific type of cubic structure. So in this case, we assume the pattern is simple cubic, or SC sometimes abbreviated. So we basically make an assumption in that case. And by making this assumption, and this is something that we can test, so even if we assume wrong, that is fine. But by making this assumption, we have the allowable values of S from the table in Colody. So basically, if I say it's simple cubic, based on those reflection rules, certain diffraction peaks, certain HKL values will be allowed. And so for simple cubic, as an example, this is 1, 2, 3, 4, and 5. So that's for the first 5. So that tells us what the S values are. And remember that these S values are h squared plus k squared plus l squared. So it basically tells us the values of h, k, and l by knowing S. So we assume a structure. This tells us what HKL values we're testing for. So that's step 1. Step 2, and I'll show you this table in a bit here when we get into the example. So next, so what we do is we check all the values for peaks. So we basically look at, let me sort of write this out here. So we saw before sine squared theta over S is equal to a constant, right? So we've just got S values from the first. So then we're also going to look at the theta values for each peak. So we have all the peak values, so the peak centers for each peak. So that gives us a theta value. We have the S, assuming that it's simple cubic, and so we can calculate this value here. And if that sine squared theta over S is a constant, so if all of the peaks give us the same sine squared theta over S value, then that tells us that our assumption is correct. So we wouldn't have to go and calculate the other ones, right? One thing to note, the values that you will have for your data is real data, so there will be some experimental error. So you can't expect that it's going to be the same exact number down to 10 decimals. But within experimental error, then if it's constant, then this would tell us that simple cubic. So from there, this is basically it if you've guessed right. But if not, move on to other structures. All right. So once you have that, so once you've found which one it is, you can use the equations that we talked about in the previous piece. So basically this, right? If you know, if this is now a constant, we've basically solved for this side of the equation. This is related to the experimental setup. So you'll have that as a constant. And then we can calculate A. So we can calculate A by rearranging that expression. So the next step would be to calculate the lattice parameter. Right. And so for the purposes of this exercise, we're assuming that our example is an element. So we're also going to inspect the table in Colody and see which one of the elements has the same crystal structure and same lattice parameter as our example. So we're going to cross-reference structure and lattice parameter with the table in Colody. So basically, there's a table of all the elements that give you their crystal structures and lattice parameters. So it's a very handy table. So we'll look at this in the last step. And then there's another table which gives you the S values. So as we go along and work this example, I'll show you those tables, and when you get to doing your own patterns, those will be made available in our folders. So we'll go ahead and get to the actual example. So I've got a unknown sample here that we're going to index using the manual cubic method that we just talked about. So 2 theta is given, height, area of the peaks, percent area of the peaks. All of this was gotten from peak fitting. Despacing, that is something that you'll want to calculate using Bragg's law, because if you rely on the computer or what the initial software gives you, they might be using the wrong lambda value. So this is for this experiment, for this example, we're going to use a lambda of copper K alpha, which is this 1.5406. So using that, we're going to calculate despacings, and we can do that from Bragg's law. So if you kind of rearrange that expression, you'll want lambda, and then you'll divide that by 2 sine, and then this is 2 theta, so you always have to remember divide by 2, right? Because Bragg's law is in terms of theta, this is given in terms of theta. One other thing that you'll probably need to know is that these are in, the values I have are in degrees. And so oftentimes your spreadsheet will not like that. And so let's go ahead and convert this to radians. So if we take this as degrees, and then our conversion factor is, we should have, what is it, 2 pi, or just pi, divided by 180, right? So that should cancel out, and that should give us radians. All right. And then let's go ahead and go back here and change the, instead of using A, we'll now use the one with the radians. So let's see how that works out. There we go. And then you might have to change this a little bit so that this doesn't change. All right, let's see if that looks right. Yep. All right, there we go. So we've got the despacings. Okay, so this is just, we've got some initial data about our peaks, and this is what we're going to use to manually index. So you'll remember from the steps that we did, the first thing we want to do is look at those sine squared theta values for a given structure. So I'm going to make another column down here that's sine squared theta, and I'll calculate that, and I'll use, again, divided by 2, and then square it. Lots of parentheses just to make sure. All right. So these are, and maybe I'll, just to make this clear, I'll put this down here so you can keep track of which peak is which peak. All right, so we calculated the sine squared theta for each of the peaks based on the theta value. And then the next part we need to know is we're going to make that assumption of what structure we have and the S values. So we're dealing with cubic structures, and so let's say the first one I want is a simple cubic, right? And this is going to give us, this is going to give us the sum of squares term S. Having a little difficulty here. All right, and so again, those S values we obtained from the table. So I'm going to stop here and switch over to the table so you can see that. On our Canvas website in the Files section, so if I go to Lab 2, XRD, and then I go to Further Reading, you'll notice I put a lot of information there from Colity because that's a really good X-ray diffraction reference. And so the first table we're going to look at is this Colity quadratic forms. And we'll wait for it to load. Hopefully. Let's give it another shot. There we go. I apologize for the delay. So these are the quadratic forms of the Miller indices for a number of different systems. But the main thing that I want to sort of draw your attention to is the first one, h squared plus k squared plus l squared. That's what we defined as S. So basically these are the S values that are possible. And then if you look over here, we have cubic, which is good because that's what we're looking at. Simple, FCC, BCC, diamond. We also have hexagonal. We won't deal with that right now. But if you look at, and you'll look at these various HKL values, you'll see that here we have values here, here, here. Basically the first 6 until we get to 7 are taken up. So those are the allowable S values. So basically we have 1 through 6 as the allowable S values for simple cubic. If we were dealing with face-centered cubic, you'll see that there's no listing here for 1, 2, 3, and we don't, it's not until, or sorry, 1 or 2, it's not until we get to 3 that we have a value. So the first allowable S value for face-centered cubic is 3, then 4, and then we don't have another one until 8. So the S values have a different sequence there. So that's what's going to differentiate the different structures. So now we have an idea of where these S values come from. We want to put in what the S values will be for the first 5 peaks, because we have 1, 2, 3, 4, 5 peaks. So we want to find the first allowable 5 peaks or S values for the simple cubic structure, and I changed that to SC to simplify it. So if we go back here, you'll remember that for simple, it basically was 1 through 5 were the first values. So I can go ahead and say that if this is simple cubic, the first S value should be 1, second should be 2, third 4, third 3, and 4 and 5, etc. So while I'm here, I might as well go ahead and enter the other values as well. And so again, I'm just scanning through this list and noting what the allowable HKL values are and translating that to an S value over here. So I've got that, and let me go ahead and input these. So BCC should be 2, 4, 6, 8, 10 based on that table. FCC should be 3, 4, 8, 11, and 12. And then for diamond cubic, that was 3, 8, 11, 16, and 19. So each of these would be an assumption that you're saying the S values are this, 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 or this. All right. So so let's start with the simple cubic. So now I want to basically calculate sine squared theta divided by S, right? Because that was the equation that we saw in the initial setup. So all I do is take my sine squared theta and then divide by S for simple cubic. And it's as simple as that when you have the spreadsheet, and then you'll just bring this down to follow the calculations for each one of these. So dividing each peak by its corresponding S value, assuming simple cubic structure, and I've got these values. Okay, so the next step, if you'll recall, is that we've calculated these values, and if this is the correct guess or assumption, then the sine squared theta over S is equal to a constant, and that's in terms of lambda and the lattice parameter. So we'll look at these, And we do notice some difference, right? This is 0.1, this is 0.07, 0.095, 98, 85. So they seem a little over the place. And so if you're not clear what the sort of allowable error is, then maybe we should look at the other ones. So let's go ahead and calculate the same thing for the other structures. So let's say I want to assume it's BCC, and so I'm going to use these values, and I divide the sine squared theta by that value. So I'll take that in the same way I did, but using the BCC values, and I'll continue this. And again, we have values here, and we want to compare if they're the same. So these, again, some of them look pretty close. A couple other ones maybe a little further apart. And we don't really see, maybe as much variation as we saw here. So let's keep going. Let's see if any other ones make sense. So FCC, these values divided by the ones for FCC, and continue those calculations for all the peaks. And you'll see that in this case, all the values are starting to get a lot closer. There's some variation, but all of the values is 0.036, 0.0359, 358, 358 again, 358 again. So they're pretty close. But again, if you're not sure about the error level, let's calculate some more. So let's look at diamond cubic. So the point of this, if you're kind of getting this, is that once you develop a spreadsheet, then you don't necessarily have to just say, let's look at simple cubic and calculate those values. You can do all these calculations ahead of time. Just have the spreadsheet set up, and then that's ready for you. So you don't have to necessarily assume one at a time. You can look at all of them and compare. So looking at these values, you see again, they're getting smaller. Some of these at the end look pretty similar, but these two at the beginning show some variation. So of the four, this one really looks the closest, right? These look the closest. So if it in fact is a cubic structure, then this looks like what we have, right? So that's what we're doing with this. We're comparing these different sine squared theta over s values, and when we see consistency among an assumption, it tells us that that assumption is most likely correct. And again, these values are pretty close, right? If you compare, you can obviously go through and look at the standard deviation or something like that, but this is definitely the best fit of the four. Okay, so let's say that we have our answer there, right? So we know what we say that the sine squared theta over s is a constant, right? It's this value. And so what we're going to do now is take that original expression for sine squared theta equals s equals to lambda squared over 4a squared, and we're going to set that up so we can solve for the lattice parameter, a. And this is going to be in units of angstroms. We're back, and I've went ahead and calculated the lattice parameter by rearranging the expression that we had for sine squared theta over s, which equaled the constants. So I've rearranged that to solve for a, the lattice parameter, using our lambda and sine squared theta values here. So you'll notice that each peak is going to give you a slightly different lattice parameter. And so we'll talk more about this in the coming week, but obviously different peaks will give you slightly different information. There's some error associated with this. So generally what you see is that there's more variation in the early peaks as opposed to the late peaks. You see the late peaks here are more consistent. They're much closer to the 4.07. So when you're looking at the peaks, and this is something you'll see in the peak fitting videos, is that those peaks and the higher 2 theta values, so if you go back here, these are closer to 90, those tend to be much more broad, and so they tend to give you more reliable values of the lattice parameter. So in this, I would say that the ones here later are more accurate than the early ones. So I wouldn't necessarily just take an average or take the first peak. I would probably lean towards one of these later ones and say that our value is close to 4.07. Because again, these peaks tend to be broader and give us better information. So that's just kind of a note about the variation that we have in this lattice parameter. So I would say trust the later ones a little bit more. Don't necessarily just take an average of all the values, because the ones that are narrower, lower 2 theta values will give you a little bit more variance than the others. All right, so let's say we got a lattice parameter of 4.07. We know that if our assumption is correct, it's FCC. And I told you in the sort of setup for this exercise is that this is an element. So what I'm going to do is we're going to hop back over here and close this out. And then you'll see that I have some other tables here from Colity. If they open. There we go. So this table, in Appendix 5, gives you the crystal structures of some of the elements. And so if this material is an element, this is going to show us. So you'll see that the type, so they're basically listed in alphabetical order of the elements, and then the type of structure, and then the lattice parameters are given here. So 4.07 is going to be a lot less common than the FCC, right? Because there's a lot of FCC metals. So basically what I'll do is just kind of scan the last parameters and see if I see anything close to 4.07. And then if if I find one that's close, I'll go over and look at its FCC. So, and then I'll just kind of narrow them down like that. So again, I'm looking for 4.07. So you'll notice right off the bat, the second one is 4.05. Right? And so that's aluminum, which is also FCC. So this is a viable option. And so I'll keep looking though, because there can be multiple things that are close. And you'll see that I have a couple in the 4s, nothing close. Then down here, I've got 4.0786. So that's really close. FCC, this is gold. All right, so gold's an option. And I'll keep looking. Nothing super close. Go over here. Keep scanning and looking for the 4.07. Here's one, 4.0863. So again, really close. It's FCC as well, and that's silver. And this one is a little further off, and it's also BCC. 4.4, it's hexagonal, so no. All right, so it looks like those are all the possibilities. So it's either aluminum, gold, or silver. So of those three, 4.05, 4.078, and 4.086. So gold is the closest of these. And so if I have to pick, which is I guess the issue here, is I'm going to pick gold, right? And so its lattice parameter was 4.07, and then, forgot it already, 86. Right? So pretty close to what we had here. So I'm comfortable with that. But again, keep in mind, there was some others. And the point I want to try to make here is that from the data that we have, it tells us that gold is the closest. But as you might suspect, if I have a bar or a powder of aluminum, gold, and silver, there's other ways that you can determine the differences between them. And X-ray diffraction doesn't necessarily tell us a lot of information about the composition. So from what we have here, the closest match is gold, but those other two are very close, and we can't necessarily rule them out. If there's some issues with maybe the purity, for example, then that can change the values. So X-ray diffraction is very important and powerful technique to getting what crystal structure we have, the lattice parameter, but without composition, sometimes we can't make that next step. So knowing the composition would be very important. So just kind of leave it there that oftentimes we need a little bit more information than just X-ray diffraction. So, but chances are, if you saw these samples, you would be able to tell of those three what we have.